Hi, and welcome to the software tutorial for Python. We will be using Google Colab or Collaboratory for Python in this course, and I'll show you here how to do it. So first of all, if you are in Google Drive, it looks somewhere similar to this. You can make new Python files or Google Colab files by clicking New and then finding Google Collaboratory. When you then create the file, you'll get something similar to this if it's a completely new one. So here you will have coding blocks or coding cells, and you can also add in text cells. So they look like this. And here you can write longer text, whereas this is mostly for coding. Worth to note is that the text files or text blocks, they use Markdown. So that's a specific way of writing text. It's very easy. If you just write, it'll be fine. If you want to do like bold or italics, there's something specific for that. For example, if you want to make things bold, you can click here, which will help you with it. So you specify what text you want bold. So that's here. So if we then go to the software tutorial, so I have written up a software tutorial for you, which I will share in the schedule. And so this file here, it contains all the things that you should know for this course. So it contains all the different functions and how to write those functions. So it's easy to copy what you want into these functions and then use them. So here you can also see, there's a quick guide on how to use Google Colab. So first of all, we have the Markdown language, which is how you write text. So for example, for this block here, when you're writing it, it will look something like this. So you have to specify with like the bigger text. You can specify that with the hashtags. You can make lines with hyphens and links and so on. And you can create new cell blocks by either clicking here. That's like the code blocks and the text blocks. You can also, when you hover above or below the text blocks, there's also these here. They can add. And then finally, you can delete the text blocks over here if you click on the delete cell. So yes. So here we have the Markdown. You can make tables if you just write it. So they'll look something like this with the lines that you have to make yourself and then text. And if you write this in the Markdown, then that will become a table like this. So what will we cover? We will cover the things that we have learned in the lectures and assignments. So you'll get the functions for those in Python, which is a widely used coding language. You'll also learn how to do the things from the measures lectures by Daniela. So that is these. So you'll cover risk ratio, risk difference, and numbers needed to treat. And you'll also have visualizations and hypothesis testing, and also the standard stuff. So, but before we start, we need to know how to load or import our data into Google Collaboratory. So first of all, you can use this code here. So it's specifically this code. So this code will allow you to upload files directly from your computer. So when you run it, you'll be able to click here, choose files, and then you can pick which file you want. That can be a CSV file, a text file, or any other files. For our use, we usually use CSV. So that's the comma separated files. And those are easily used. We can also link our Google Drive with Google Colab. So here you use this function for that. Then you can link the drive to the Google Colab, and then you should be able to see the drive over here. So that's a little folder file, and then you can pick, and then you'll see the Google Drive here, and you can then easily work with that. Something worth noting is that because this is all run through the browser, also Google Colab, you need to relink your Google Drive every time you use, or every time you have closed Google Collaboratory. And that's the same with the files, so you also need to upload those every single time you have a new session, or you close it and restart it. You can also, so when you have loaded your file in, you need to be able to read it. And one way to do that is making it into or using the library pandas. So these are the libraries that we use. So that is also something that we can import. And that's something we need to do every single time we use the file. So that's something we do every single time we use the file. So this is pandas, and we load that as PD. So we specify that the package pandas, we need to call that PD in our functions. So that's what we do here. It's the same with when we are using the Google Colab file or package. So that's what we have here. And we also have that for the file section here. So these are all where we specify that this is a package that we want to use for this Python. So yes, here we have the pandas, and we specify we want to read a CSV file. So we, so this is the file that we just uploaded. So either through Google Drive or through upload files. So we can read the CSV file that we just uploaded. So here we need to specify the name of the CSV file, and then we can load it in. And here we then save it to a variable, or the name, df2. So the name of the CSV file, so this file here, it'll be saved to this. When the data files are loaded in through pandas, so using this function, it will be saved into something we call a data frame. And that is a data structure which organizes the data into tables with rows and columns. It's very much like a spreadsheet. It's very common data structure that we use, and it's very easy to use that. In case that we also want to manually enter data into a data frame, we can do that by writing this. So again, we can specify pandas as PD. So we use the package pandas. This is also, so these lines here is also something that you usually only write once at the top of your document. So you write all the different packages that you have in the file, and then you don't need to write it again. But here I have written it in multiple cells just to make it clear that that's something that we use. But yes, so we can make our own data frame by writing this here, this block. So we're saying that we have a data called data1. And in data1, we have a person ID, which is these here. We have some sex that we specify. We have ages, and we have diabetes, yes and no. And then you can say that using pandas, we want to make a data frame using the data1. So that's the one that we just made here. And it's important that you have the same number of values or variables in every single or every 4 here groups. So that needs to be, so here there's 20. You also need 20 people here, patients or people. You also need 20 here and also 20 here. Otherwise it can create some errors. So when we have made our data frame, so our data structure with data in it, we can call this by specifying or just writing the name of the data frame or data structure. So here we call it df2. You see, that's df2 here. And then if we just write df2 and then click enter or click run, then that will output your data. So this is the data that we just made. So we have 20 rows, 20, there should be 20 patients here, unless I forgot a number. And then you have the columns with the different data. With Python, they also count 0. So they usually, whenever they start, they count 0, 1, 2, 3 instead of 1, 2, 3. So that's something worth to note. So this was the basics of how to create the data or upload the data that you want to use. Then we can go to the mean, median, and mode, which are some of the things that you learned during the statistics. So how do we do that in Python? First of all, whenever we want to calculate something, we need to specify what it is we want to calculate. So for example, if we use the same data set that I just created, we have age. And if I want to specify that we calculate the things using the age, or how can I say, want to find the mean, median, or mode of the age, then we can specify that with the function writing here. So we're saying this is the name of the dataset, so df2, which was the one I created here. You can see this is df2, all of this. And then I specify within df2, I want age. So that's what I do here. And then we need to remember these small colon thingies. So we're saying df2, I want the age. And then after that, I can use the functions. So the functions for the mean, median, and mode are these. So it's mean, median, and mode. And then the whole function would look like this. So this is the one for the mean, this is the one for the median, and this is the one for mode. So we're saying in the data set df2, we want to use age, and we want to calculate the mean of that. And when we then run it, if you don't specify, so here, this is a print function. So here we write some text before, and then we have our function. And this is just so we get this text. Otherwise, you'll only get the number. So if you just run the mean function, for example, you'll only get 28.35 outputted, or out here. So this is why we can also write the print function. So the print is basically you can write any text here. You can write print hello world, or print this is a PC, or print this is a computer. You can write anything, and you separate the things. So here we have this is the mean of age, and you specify it's the text using the colons, the quotation marks here. So you need that both in front of and at the end. So you write the text, and then you separate the things, the different blocks in the text with a comma. So you have this is the first part, and then you separate. This is the second part, and then you'll get this. And you can do the same with median and mode. Then in the statistics, we also covered variance and standard deviations. And similar to how we calculate that. So similar how we calculate with averages with the functions. You also have some functions for variance and standard deviation. Here we just have to use a package. So that's a statistics package. So statistics package is part of the default packages in Python, but you need to specify that this is one that we use. So that's what we do with import. So if you don't import it, then you can't use it. And then you can write it here. So this is the variance. We name a variable called variance. And then we can say that the variance is equal to, this is the package that we use. and then this is the function. And then in that, you specify that you want it for this data set and this variable. And then you can use the print function to output that here, just below. And the same you can do with standard deviation. So here we create the standard deviation in a, I would say, give it a name, and then we use the function, and then we can output it. If you don't give it a name, it'll just directly output the number without anything else. And so this is mostly so it looks better. So now we'll move into the visualization. So how we can give some nice charts and graphs for our data. These are the ones that we covered in the lectures. There's more information regarding graphs and charts here. So this one, it contains a big gallery of a lot of different graphs. Some of them are very fancy, so you don't need to know all of them, but there's just a lot here if you want to see other kinds of charts. So we start off with the scatter plot. That was also the XY plot, so where you have the x-axis and y-axis, and then you have some numeric variables on those two axes. So for this, how to say, demonstration, I'll just show you using a public dataset called IRIS, or the IRIS dataset. So that is a well-known dataset from 1936, and is usually used for machine learning algorithm and visualization. So it's a dataset about the different, three different iris flowers. So we have the setosa, various color, and virginica, and then it got some some other variables, so sepal length in centimeter and width, and also petal ones. So that is what we have in the dataset. There's 150 rows in total, 50 for each of the species. So this is the IRIS dataset, and it's public. So first off, we can import a library called Seaborn. So Seaborn got a lot of different functions for visualization. So for a lot of these things, we can use Seaborn. First of all, we also need the IRIS dataset. So within Seaborn, the IRIS dataset is also saved in, so you can load that through the Seaborn function here. So here, as we said, we say Seaborn is called SNS. So we want to, you can call it anything else too. You can call it C, then you just write C here instead, and then this would also become C instead. But now use SNS. So we specify using the Seaborn function, or within Seaborn package here, we need to load a dataset called IRIS. So IRIS is also saved inside of Seaborn. It's also saved inside a lot of other different packages. And then we, the IRIS dataset will then call DF. So that is how we can recall or call our IRIS dataset. So first of all, we want to see the first color rows in the dataset that we just imported. So we can use df get. So this means that we just want to see the first couple of rows in that. Df is our file, or our data, and head is the function. So then we get something like this. You see some of the row numbers here. You see the different variables or columns that we have with variables. And then this is the species. If you then see more of the species, you'll also get some of the other two. But this is just because we just have the first couple of lines or rows that we only see one kind of species. So to make our scatter plot, we just need to use this function. So again here, we specify this is from the Seaborn package, and we want to use this function called a rig plot. In this plot, so this is what we use to make our scatter plot. In this scatter plot, the x-axis, or the how to say, so the x-axis is the sepal length. This is what we specify here. So you say this is a data set. This is what we want to plot on the x-axis within the data set. So that is these here. So 5, 1, 4, 9, and so on and so on. And then on the y-axis, we want sepal width. So these are here. You also specify y-axis equals, so y-axis is the data set. Within data set, we want to call this variable. And then we have fit reg equals false, which is just to say that we don't want a regression line in our data set. So that is the line where you have all the different variables, and then the best line through that. So the line where the distance from the points to the line is the smallest for all the different points. So we just say that we don't want that, and that's what we can do with this. And then we get this nice scatter plot outputted. So we have all the different numbers on y and x axis, and then plot it here. So for example, 5, 1, and 3, 5. So that will be somewhere around here, and then there will be one of these points here, because those are corresponding, or those are together, and that's what you get for all of these different points. Now we can move to box plots. So this is also something that we can easily create. Again, we can use the Seaborn package. And here, if you want to read more of it, there's a link here. So this is for boxplot specific. So again, we can specify a Seaborn, and we want boxplot. And then we can specify what the x-axis should be. So here we have the different species, also different categories within species. And then we can also specify what y-axis, or what it should be plotted against. So here we have the sepal length, and then it will be something like this. You could also, this in other datasets could be such as which treatment it should be, or which treatment it is, or what sex, and so on. So this can be basically anything. If you don't want the different categories, you can also not have those by leaving this leaving this x part out. So that's what we have here. We have the Seaborn package. It's a box plot, and then we only say y is y equals to the sepal length. So that's what we have here. That's just one big one with all the sepal length, not specifying which class it is. Then we can make some histograms. Again, we use Seaborn. This is a link for more information if you want that. And that function looks like this. So we write this plot, and then you write what variable it should be over. So here we have sepal length, and that's how you write it. So a equals this variable that we want, and then we can say it's a histogram with true, and then there's some other functions that I have taken as false. Those are functions that give you other things in this graph. So for example, a line over everything, or a density plot, or something like that, which is something you don't need right now in this course. You can also specify how big these bins should be. So that is what you can do with this. Its bins equal, for example, 20. So here say I specify that I need 20 bins, and then I get that for this function. And this is a number that you can play around with yourself also, if you want. This is the default. The first one here is the default that Python gives you. So where you don't need to specify the number of bins. If you do need to specify the number of bins, you get something else, something like this, for example. And then additionally, in addition to these charts here, you can also combine some of them. So for example, here, you can combine a box plot with a histogram, and that is done with function here. So first we say we want to import Seaborn. Matplotlib is a standard graphing or visualization package that you can also import. So this is something we need to do if we want to have both in the same graph or chart. So here, first we can set, this is the background for these charts. So for example, if you see here, it's a bit more darker than the one up here, because here we didn't specify background, and the one up here. So that's what we do here. We specify it should be a bit darker, and then again we can use the iris dataset. You only need to load the iris dataset once. I've done it multiple times just to be sure that I had the correct ones. And I saved it to this name, and then first we can create we can create two objects, so two names. We'll give it two different names, and we say there are two plots here. So there's two plots. Those two plots should be called that's plot box, and that's the histogram. And then we can select or also specify the grids, so how far they should be from each other. This is also something that you can play around with. And then you create the different box plots. So this is first box plot, or this is the box plot, and then this is the histogram. You say this is belonging to the box, so the one that we also had up here, and the other one is belonging to histogram, the one we have here. And then we can combine those two by, or we can show those two because we already said that this is part of the same plot with this function by plt show. So we're calling the matplotlib library or package and saying, hey, show this function that we just made, or these graphs that we just made. This here is just to remove these x-axis layers or labels from the box plot, because otherwise you will also have another axis here which says the same as this one. So you just have two of those, and that's what we do with the remove this here. So we're saying there should be nothing in this label up here. Then we can also go to pie charts. So pie charts is something we also covered in our lectures. And more information can be found here in this link. So unfortunately for the pie charts, we can't use Seaborn, so we need to use the matplotlib library. Again, we used iris dataset. Unfortunately, with the pie chart function, you need to also specify the proportions. So for example, for the iris dataset, we know that there are 50 rows, or 50 rows for each of the different species. So these are the categories we have. So we know these are the proportions, 50, 50, 50. And then you can write that using the matplotlib library, saying that these are the size of the groups. It's 50, 50, 50. So we save this to this name here. And then you can create the pie plot using the plt, which is the package here, and then pie, and then here you specify how big the different chunks should be. And then you can show the graph or the pie chart using plt show. So we can also add some more information to these charts here. So for example, names and stuff like that. That is what we do here. So we can say the pair names, they are Tosa, Vesicola, and Virginia. And then you can specify that in the function. So we write here The first one was the size of the groups, which we also used in the previous one. We have labels, so those are the pie names that we specified here. And then we can also specify that we want percentage for the different parts of the pie chart. So that is what we specify with auto PCT function. So here we say they want 1 decimal for the percentage, and that's what we get here. And then you can give it a title with the PLT title. We call it awesome pie, for example. And then you can also say for the axis, we want it to be equal. Otherwise, it can get some weird shapes. So that's what you get from this. If you didn't have equal, but instead, for example, had auto, you would get a not so circular, not so perfect circle pie chart, like this, for example. So this was the different visualizations that we have learned about during the course. Now we'll move into the hypothesis testing. So here we have t-testing and chi-square test, which are ones that you learned during the course or during the statistics part. For this, we want to use a package called research py. Unfortunately, this is not one of the base packages in Google Collaboratory, so that is something that we need to install first, and that is something we can do with the pip install and then the package that we want. So you can also install any other package using this function. This is also something you need to do if you have Python on your own PC. You just need to install it once and then you're fine. Here we need to install it every time we use it because we're using it through Google Collaboratory. So it only saves the things once. Save it when you use it, and then every time you close it and then open it again, you need to reinstall it. So first we install the function here, the research py, which is a package for hypothesis testing. And it got a lot of functions for that, and also for academic research in general. You can go into research py's website if you want to see what other things it have. So we install it, and then as before, we import our function research py, and we call the rp here, just so we don't need to write out this whole name every single time we use it. We also import another commonly used package called numpy, which is here, and we call it np. And then we have pandas, which we have used before. For this example, we'll use some public blood pressure data. So this is something that we can find on the internet. We can directly get the data from the internet by just linking to it. So here, if you can see, you have the PD, which was the panda function. We want to read it as a CSV file. And then instead of giving, so before we had uploaded our data and then we had referred to the data name, here we can refer to the link on the internet. So this is what we do here. And then this function will just get it directly from the internet and then load it in to this name here. If you want some information regarding the data, you can type in info after the name of the function. So that's what we have here. And then we get that there's 120 rows for each of these. You have the columns of variables: patient, sex, age group, blood pressure before and after, and then what kind of data type it is. So for example, integer. So there's no decimals in these here. So now we have our variables or data set in. We can make a t-test on that. So in the research pi package, there's a function called t-test. And for this specific t-test that we want to use, we want to see, or we want to look at the mean difference in the continuous variable blood pressure between the groups of sex. And here I'm specifying that it needs to be the blood pressure after. So again, we have the package rp. This is the function t-test. And then we specify, okay, in the first group, so this is group 1. These are the data that we want to use, or the variables or values. And this is the sex group that it needs to look for. So in group 1, from this data set, look at these variables here, or these values for the blood pressure after, and it needs to be those with the sex male. So that's what we specify here. And then we can also call the group name male. So that is what we get here. Otherwise, you'll get 1 and 2, which 0 and 1, which is not that informative. We also need to specify what the second group is. So that's what we do here. Group 2 equals this. So that's the female ones. And then we get this output. It contains, so for the specific variables for the males, you have the mean, you have the standard deviation, standard error, and you have the confidence interval here. You'll also have that for the females, and you have it for the combined one of these two. And then below that, you have the t-test that we just want to calculate. So this is the difference between those two. You also have the number of freedoms, or degrees of freedoms. You get the t-test value, and you get the p-value. So this is the two-sided one. So just is the difference between those two. And you can also see what the p-value for only one of the sides are. Here. So for example, the difference is below 0 or the difference is above 0. Then also you'll get effect sizes, so cohens D and HG. This is also something we can calculate further below, or we will calculate further below. And then here there's a bit more text if you want to read about it, because I will share this file with you guys. Unfortunately for this here, so using the RPT test, you don't really get a confidence interval for the difference. So that's something we can do or calculate manually with another package called Penguin. So we install the Penguin package. So that's what I do here. And then we import Penguin as PG. We specify the different groups, so group 1 and group 2. And then we can say that we want the t-test and confidence interval for that. So that's what we get here. This is another function that you can use for the confidence interval for the t-test. It gives you the t-value, degrees of freedom, p-value, effect size, and also power. So this got some other output than the other one. But so the results for both of them is the same. You just get some extra information here. If you want to do a paired t-test, so for example, if you want to see in the same patients at different points in time, you can use the paired version of the research PY package. It looks very similar to what we wrote before, but here we just have group 1, which is the before, and we have group 2, which is the after. And then we specify that this should be a paired test by using paired equals true. And then we get these values here. You also get for this one the confidence interval. So this is not so we didn't get that for when we had 2 different groups. But we do get it when it's the same patients but at different points, so a paired t-test. And again, you get the variables and the mean, standard deviation, standard error, and confidence intervals for the different variables. You also get the difference and degrees of freedom and also t-values and stuff. Then we can go to the chi-squared test. So that is what we have here. So just for demonstration purposes, I have made some data. So that's what I do here first. I make some random data, and we call these data variables disease, severity, and alive, just to have something that we can calculate it for. We specify there should be 3 levels, and then the size of them. So that's what I have here. So there's 101 row in each of these. and then we'll have 3 variables: disease, severity, and alive, spanning 0, 1, and 2. So that is what we see here, and I saved it to this df name. So then we can make a cross tabulation. So that is also something we did talk a little bit about in the lecture, in lecture 3, about hypothesis testing in chi-square test. So, but these are made very easily using crosstab function. So research PY, this is the package. We have the function called crosstab, and then we can specify which variables it should be with. So for example, here we want diseases and alive status, or stage, or just this category. So this is what we get out. We have diseases here, and we have alive here at the top, and then the number of patients in each of these groups. So for example, alive 0, disease 0 is 10. That's 10 patients. Or alive 2 and disease 2 that's 7 patients in this group. You get the total number for the rows, you get the total number for the columns, and then the total in patients in total. So this is our crosstab. Then to calculate, or to make the chi-square test of independence, so when we have 2 groups or 2 variables, we need to specify that's a chi-square test. So we use the same crosstab function, but here we then, in addition, also write that it should be a test, and it should be chi-square test. And we still use the same disease variable and a live variable. So first we get this crosstab again, which we got up here. And then below that you'll get the chi-square test results. So you get the chi-square is this, you get the p-value, and then you get a effect size for the chi-square test. Depending on how many categories you have, you get either a Cramer's phi or Cramer's v. So that's what you can see here. Both of my effect sizes. This tab though is, or this output is not really pretty to see. So you can actually specify, or you can split the first part here with the cross tabulation, and then split it from the chi-square test results. So that is what we do here. We say there's a crosstab part, we say there's a results part, and then these two, so the cross tabulation and results, equals to our function, the crosstab function from the research py package. And then we can call the cross tabulation first by just specifying the name. So you get this cross tabulation. And then secondly, you can get results by just writing res. So this is what we call the results. And then you get the results for the chi-square test. You can also calculate the expected frequencies. So if we do it using the prettier way to do it, again, we have specified crosstab, we specified results, and we specified you also have expected frequencies. And then that is what you see here. So this is the expected frequencies. We want that. So we say expected frequencies should be true. That means now we get expected frequencies. And then we can output that. So only the expected frequencies, and then we get these numbers here. These are the frequencies for the different groups. Cool. Now we can go into the power calculation and sample size. So specifically for here, we use for the power calculations, we use the code from this website called Geeks for Geeks, Introduction to Power Analysis in Python. It uses, so first we need to import some packages. So we have math package. We want to import it so we can do square roots, because that's not part of the default. So you need to specify square roots, so you can use those. And we also specify from this package called stat models that we want to import this specific power analysis function. So first, if we, for this demonstration purpose, also just make up some data. So here we first specify we have 2 samples, and these have the sample size of 4. So this is the first sample, this is the second sample, so group 1 and group 2. We can also specify the variance for these samples, so that is sample 1 and sample 2. And then we want, so this here, actually, I can show that's a picture. So this is how you write exponentials. So for example, this is 5 to the power of 2 instead of 3. So that is how we write this. The 5 to the power of 2 is this here. So that's just quick guide on that. Cool. And then we want to calculate pool standard deviation. So for coherence D, the effect size, we need the pool standard deviation, and that is something you can calculate with this. This is the same function that we also have in the medical statistics book, or medical statistics at a glance book. So it's just written up as a function here, so it's easily calculated. So as long as you just specify these here, the number of samples and the variance, then you can calculate the pool standard deviation using this formula easily. Then we can also specify the means for the samples. So for example, in group 1 we have mean 90, and for sample 2 we have mean 85. Then we can calculate effect size, so the differences in means divided by the sample, the pool standard deviation, and then we have the effect size, which in our case is 1. And then here we specify just quickly what alpha values should be. So that's the 0.05 or 5%. And we also specify the power. And then here is just a very quick guide or more information about the exponent or exponentials. And also for the coherence D effect size. So that's what we see here, the difference between the 2 means. And then this is the formula for coherence D, so the effect size for coherence. We have the mean of group 1, mean of group 2, and the pool standard deviation. Also something that is very similar to what we have talked a bit about in the lectures. So yes, prior to conducting studies and trials, it's also important to calculate the sample size, so we know that there's enough power in our trial or study. And that is something we can do using the following function here. So here we specify, so this is the function we had before that we imported. We want to say, or we want to make it a bit shorter because this is very long to write out every single time. So we can say this function should be called obj or object or whatever you want to call it. And then we can easily refer to this part as this here. And then within this function, we need to solve the power to find the power. So this is just a function called solve power, but it can also be used to find the sample size. So we can, we can put in all our parameters. So we have the effect size, which was D. So that is what we had up here. So D, effect size. Then we also have alpha, which we specified up before, which was 0.05. We have power, which was 0.8. And then ratio is the ratio between group 1 and group 2. So right now the ratio is 1. So that is when you have exactly the same amount of people in group 1 as you have in group 2. Otherwise, you can find the ratio by dividing the two numbers with each other. And then we can say that it should be a two-sided one. So that's what we specify with this. and then you can output it. So here we just make it a bit pretty. We say we have some text, and then we should output this number of samples using 3 decimals. That's what we have here. That's the format part. And then n is what we have here. So this is the number we get from this test, or this function. So specifically for here, we need 16.7 in each group, which we will round up to 17 because you can't have half patients. So yes, this is with the same effect size of 1, and then the 2 different power and alphas here, or the alpha and powers here. You can also calculate the power for the test, or power for your data. So for example, so here we use the package stat models again. Instead of the test in power, we use the tt in solve power function. That's what we have here. We can then write out the function, and then the number of observations in the first group. So we say, for example, 10. We have effect size of 1, and then we specify that power equals none because we don't know what the power is. And then you can say the alpha should be 0.05, and then that will output a power value for you. So that is how you can find the power. We can also do it for proportions. So the first part here was for continuous variables. Now we can also do it for proportions. So we need to import stat models again, but another part of stat models, which is stats API, and we want to call that SMS just to make it a bit shorter. So first, what we need to do is that we need to specify what the proportions are in both groups. So we have group 1, proportion should be 0.1, and then we'll have proportion 2, which is 0.12, just to make it a bit different. Then first, we need to find effect size. So that's also something that you got in the test above when we did the hypothesis testing. But if we don't have the hypothesis testing, we can just specify here directly. So from this package, SMS, or stat model stats API, we need to use the function proportion effect size, and then here are the 2 proportions that we have. We save our effect size to the function ES, just so we don't need to write all of this every single time. And then we can use the normal in power function, and then solve power to get the number of samples per group. So for example, if we have proportion 0.1 and 0.2, we have the effect size for that, which is from this function, also what we write here. Then, and the power is 0.8, alpha is 0.05, and then we have 1 to 1. So there's the same number in each groups. Then the number of samples that we need is 3,834.59 to round up because we can't have half samples. So that's the number in each group that we need, and that's what we find from this. We can also calculate the power. So that is with the same same function. But instead of specifying the number of samples that we have, then we specify, instead of specifying the power that we have, we need to specify the number of samples that we have, and then the ratio. For example, again, if we didn't have 3,000 in each group, then we could specify that with the ratio. So we have 1 divided by the other ones. So for this, with effect size from these 2 proportions, so that's what we have here, and 3,000 each groups, then we would have a power of 0.698. instead of the 0.8, because 0.8 is that there we needed to have 3,834 in each group. And that's not what we have, so we have a lower power. So that was quickly on how to calculate power and sample size. And now we can move to measures of association, which you had a lecture about with Daniela, I believe. So in here, we'll cover how to calculate the risk ratio, risk difference, and numbers needed to treat. So first of all, we'll use the package zip_id. So we need to install that because it's not part of the standard packages that we have in Google Collaborator. So when we have installed that, we can import it, and then specifically we can load sample. So here I'll load another sample that they have available inside the zip_id package, just to demonstrate how to do it. I'll also load in the other functions of risk difference function, risk ratio, odds ratio, and numbers needed to treat function. I can print out the version of this package and also also load in the package. So that's what I do here with the load sample data. We load the sample data, and then we call it df. So the df is now our sample data, and then using df info, so the info function, we can see what variables is inside of here. So they have a lot of different variables. ID, male, so if it's male or female, age, and so on, and also det and odds, which is the treatment. And here you can see how many rows there are. So specifically, you can see there's a bit fewer with the det. So this could mean that there are some missing values. Yes, this is also public available data from this package. And if we call it, you can also see how it looks. So this is how the sample data look like. So you have like some variables up here. You can see the number of rows, and yeah, this is how it looks. So 9 variables, 546 rows. Oh, this is because it counts 1 0. So this is actually 547. Cool. And we'll use this data to calculate the different measures of association. And here is just a little bit more about the data set. So we have the therapy or the treatment. Oh, so this is the retroviral therapy, and we have all-cause mortality, which is the det variable. And this will be specifically at 45 weeks. And then therapy 1 is treated and therapy 0 is not treated. And with det is also 1 is det and 0 is not det. And then, as I said, there's 30 missing det variables, and we will ignore this in this tutorial. But there are some functions that can take that into account and also calculate using that. So first of all, using risk ratio function or formula, whatever you want to call it. So this is the function we have, risk ratio, from the package zip_id. So now we have already loaded in zip_id, so I didn't load it in again. I want to name risk ratio. I'll give that the name RR, just so I don't have to write risk ratio every single time. So that's what I do here. And then first we need to specify in the dataset the exposure and the outcome. So exposure, outcome. This is our dataset. So you say in this dataset. So this is another way to write it. Depends on the functions. But so before, like at the beginning of this tutorial, we had df, and then we had the square parentheses, and then specified the variable. Here, because it's another function, we just have to specify the dataset that we use here first. And then we specify within this dataset, the exposure is called odd. So that was one of the variables that we saw before. And we have outcome, which is det. And then we can fit this model here, specified, and then we can call the the results using the summary function part. So if you run this block like together, you'll get this output here for exposure art and an outcome dead. So that's what we also have here. We have E as exposure and D as the outcome. So yes and no, and yes and no. From this, you can then get the risk here first. So risk for outcome 0 and outcome 1. No, treatment 0 and treatment 1. And this is the risk of the outcome. So that's what you get here. And then you can also get the risk ratio for that. So the risk ratio when you have the treatment is 0.74. And then you have the lower confidence interval and upper confidence interval. And also you have, so here is the missing part. Here it specifies how many of the different exposures or outcomes are missing. So you can here see that there are 0 missing exposures. There are 30 who are missing the outcome. So those are the 30 that was missing the dead value. And then there's 0 who's missing both exposure and outcome, because they don't miss both of these two, but only one. So yes, so from this output you can see, so 7.4. So this is you can see that the 45-week risk of all cause among those giving the treatment was 0.74 times that of those not giving the treatment. So in other words, that is a 26% decrease in the risk of death among those taking the treatment compared to those not taking the treatment. We can also calculate that the risk difference. So this is a very similar function. Again, we have the function here. We call it RD just to make it easier for us to use it and not having to write everything every single time. So for example, if we needed to use the function multiple times, then we didn't need to write risk difference every single time. We just write RD. Again, we specify exposure and outcome, and then we can use the summary function just to print the data that we get from here. So for the risk difference, again, we have this table with the outcomes and the exposures. You have risk, and then you have the risk difference. So just for information, we again have the missing part here. So the missing exposure and missing outcome. You also have two risk differences parts here. So this part is a very specific one called a frigid probability bound, which I don't believe we have covered in the course. So I think we can just skip these just for now. And then we have the risk difference that we are interested in. So that's what we have here. For example, we can see that's 4.5 percentage points. I would say the 45-week risk of all-cause mortality among those giving treatment was minus 4.5 percentage points compared to those not treated with the treatment. So that's the difference below 0. So intervention is good. That's what we see here in this table. And then finally, we can move for the numbers needed to treat, or to the numbers needed to treat. So this was the number of patients you would need to treat to prevent an adverse event. So that is if intervention reduces risk of outcome, which in this case it is. So this specific one, it is preventing outcome. So here we first specify the the function. So we do this just because we don't need to write this part here. So if we call NNT equals the function, then we don't need to write these parentheses every single time. So here, as same as before, we have the data set, we have exposure, we have outcome, and then we want to print the function, the results. So from this part here, we can see the numbers needed to treat, we have some confidence interval, and then we have the number of missing data points for exposure, outcome, and both. And from this, we see that we need to treat 23 because we round up with the treatment. For the numbers needed to treat. So to prevent one death by the 45 weeks, which was part of our description from above. And then what's to note here is that the confidence interval goes from something to infinity, and that is because the confidence interval, so in the risk difference, which we see here, so we have the lower, we have the upper bound here. Because that risk interval crosses 0, we get infinity because the numbers needed to treat will become something like 1/0 because of the 0 risk difference. That's why. And then finally, we can move into an example. So I will upload a file that you can also use, so you can calculate. You can also calculate this yourself. I'll share this whole document, so it should be very easy to run everything. So this is something, this example data set that I have created is something that looks similar or fairly similar to what you get in the RCT project. So in this example, we want to investigate among patients with epilepsy if there is a difference in the risk of hospitalizations for heart failure among new users of valproate compared to new users of levetiracetam over a 1-year period. And just for information, valproate and levetiracetam, they are both anti-seizure medications. And then we have some patient characteristics included in this example data, in addition to outcome and treatment status. So for now, I just have the outcome here, but we have age, sex, and then hypertension and diabetes, which can both be related to the risk of heart failure, hospitalization. So first we upload the file. So I have already done that here. So I call it tutorial data file. I'll also upload it to the folder. Then so we upload the file here, we read in the file. As I said, we specify. So here I've called the file name tutorial data CSV. So that is the name that is saved to. And then we can use the read function from, I think one of the very first cell blocks in this file. So you just copy paste it in. So we specify the name here. And then we can see how the data file looks. So we have the patient ID, we have treatment, yes and no. So that's 0 and 1. We have some ages, we have sex, and then the outcomes, and then if they have diabetes or not, and if they have hypertension or not. You can also see some information about the data. So there are 1,000 rows for each, meaning that there is no missing data, or there should be no missing data. Then first of all, we can do some box plots just to see how the age looks for the different sex, because we want to make sure that the two groups are fairly similar, so they are more comparable. So we can see here, we plot them. 0 is female, 1 is male, in this case here. And we see that at least the two box plots, they look very similar. You can also do a histogram. So first we do a histogram of all the different ages. So that's what we have here. Looks very normally distributed. And then we can also layer the box plot on top of the histogram. Again, looks very normal distributed. And then we want to see if we also want to see the ages for the different sex with the histogram. That's what we see here. So here specifically, I have layered the sexes on top of each other. So we have both histograms for sex, females and males in the same histogram for the ages. And that's what I select with hue. So hue will give us these two instead of only one. And we can do the same for the treatments. So if you're getting drug 1 or drug 0 or drug 1, so that's valproate or levetiracetam, we lay it on top of each other. We see the ages between those two groups is fairly similar also. Then research PY was a function that we also used before. So that's one of the functions that I covered. And that's what we use here. We want to see if the ages are different or not. And we get a p-value. So there is maybe a very slight difference. If you also look at the confidence interval, they don't, or they just barely overlap, right? And then another function that we, another thing that we usually have in epidemiology and research in general is the table 1. So table 1 is usually the table that gives all the baseline characteristics for the population. And it can easily be made using the table 1 function from the table 1 package. So I just give you that, and that will look something like this here. So you get, now I also have outcome, but usually that is not in. And usually we have it for the 2 different drugs. And you also don't have the patient ID, because that doesn't make sense to have, because that's just the labels for different patients. But yes, so that is what we have here. We have table 1 function. This is our data set. So the one I made for this example, run it, we get this output. And then, as I said, usually we group these by the treatments. So I can specify this with group by and then different treatments. So that's what we have here. We have group 0, we have group 1. So treatment 0 and treatment 1. So valproate and levetiracetam. And then the number of patients in each group. So that's what we have here. The age with the standard deviation, the proportions of the different sexes, outcomes, diabetes and hypertension, also proportions of that. You can also see if there are any missing here, which we don't have in this part on this example. You can also include p-values in it. So for the differences, if there is any differences, and then the test that was used to test for the differences. Again, patient ID, we don't conduct a test on that, because that's just labels. But otherwise, you have, for example, chi-square test and t-test. Cool. Then we also want to see if our power is good enough for the study. So that's something we can do here with the proportion, like the proportions that we had from before, where we calculated the different things. So one of the functions was to calculate the power using proportions, because that is what I have in this case. So we have 2 proportions of outcomes. So for example, we have 29.5% and we have 20.3%. We calculate effect size using the 2 proportions. And specifically here, because we don't have the same number of patients in each group, we can specify the ratio, which is proportion number in group 1 divided by number in group 2. And then we input all our variables in here. So effect size, number of observation in group 1, and then the ratio, which is this. And then we get a power from that. So we can see this power is very good. It's 90%. So that is what we want. Then we can run the different measurement, measures of association test. Calculations. using the SIP ID that we also learned about. So for example, first of all, we can use numbers needed to treat. We get that we need to treat 11 individuals with our treatment. So leave it to rest of time. Oh, excellent, double clicked. To prevent the outcome of hospitalization due to heart failure. And we also get a confidence interval for that. We can calculate our risk ratio. Here we have 0.688 for the risk ratio. We have a confidence interval. So in other words, there was a 31.2 decrease in risk of heart failure hospitalizations among those taking levetiracetam compared to those taking valproate. And then we can also calculate the risk difference. So here we have 0.092. So that's minus 9% difference. So from all of these analyses in this example, it does seem like that levetiracetam has a decreased risk of the outcome compared to valproate, and that might have something to do with how the different drugs works. So valproate, it works on some of the same paths that the heart failure drugs works on, so they might work against each other, which could explain this. But yeah, so I hope this tutorial can help you or will help you, and if not, please let me know, and good luck with RCTs.